Morning, students. Myself, Vijay Shankar from ECE Department, Chevron Engineering College. Today, we are going to discuss about the relation between the current and current density in the third unit of electrostatics. The relation between current and the current density, we know the I is equal to the integral J bar dot ds bar. I is equal to integral J bar dot ds bar. In yesterday class, we completed the relation between of current and the current density, that is I is equal to integral J bar dot ds bar. And now the relation between the J bar current density and the rho v. The relation between current density and the rho v. The rho v is the charge density, the volume charge density. So in this, the set of charge particles give rise to charge density. The set of charge particles give rise to the charge density in a volume V. The current density J bar can be related to the velocity with which the volume charge density, these charged particles in the volume V crosses the surface at a point. So let us see here. The surface we have S, and the charged particles passes through this surface with a velocity having, that is a Z bar is there. The charge density, current density is Z bar, having some velocity. The velocity with which the charge is getting transferred in V bar meter per second, it is a vector quantity. To derive the relation between J bar and the rho v, consider a differential volume delta V having a charge density rho v. Consider a differential volume delta V having a charge density rho v. We know if there is any charge in the volume, means definitely change of dq by the dv is equal to, we know, the charge density, volume charge density rho. Now I'm assuming is in the differential, a small change of the charge, with respect to the small differential volume dv is equal to rho. Now, there is a relation between these two. To derive the relation between the J bar and rho v, consider a differential volume delta V having the charge density rho v. The elementary charge carriers, you see these are equation we got delta Q, not the del, it is delta Q. Delta Q is equal to rho v into delta. Rho v into delta V. Small differential charge with respect to the volume. Delta Q is equal to rho v into d. Got it, my students? Now, see in this diagram, the incremental charge moving in x direction. The incremental charge moving in this is a surface we have. On that there is a small incremental surface, and the charge is there, delta Q. You know the delta Q is a rho v into dv. There is a moment occurs in the x direction. This is x direction, positive direction, participants. This Z is a positive direction, AZ bar, and the y is also is a positive direction, AY bar, and here the x direction having the base vector is also the AX bar. So from the origin to the towards the positive x direction changes the delta V. There is a distance of the charge, it is a delta V, and here there is a delta X it is. Okay. You know the delta Q is equal to rho v dv. In this direction is a Z direction, Y direction. Actually, we have the three sides is a differential incremental surface and the incremental charge, and it having the incremental length dl. Now it moves in the x direction. In the x direction, the change is delta x. Move in the positive direction, the change is x direction. Some displacement occurs here. Okay. Now let dl is the incremental length while ds is the incremental surface area, hence the incremental volume. Hence the incremental volume. We are saying it is actually, if there is any line is there, that is a length. There is a surface we have, that is we'll consider it as a delta. Let us take it as a small incremental length, and the surface is a delta s. And combining these two functions, okay, combining these two functions, we'll get it's actually this not here. Let us take this one. Okay, this totally becomes a volume. Got it, my students? So delta s and the delta val, product of these two functions will be nothing but the incremental volume delta v is equal to delta s into delta l. Got it, my students? So I'm taking the line at having the incremental L and surface is a incremental S, only the one side if I'm taking. Combining these two, we'll get it the volume, delta L into the delta S. So delta V is equal to delta S into delta L. Okay, observe my dear students, how we got this equation. V is equal to S into L only actually. Got it? And delta V is equal to delta S into rho L, and we can substitute here delta V. Delta V, what is the formula? We have the delta Q by delta V is equal to a small incremental is a rho V. Okay, delta V is equal to delta Q by rho V. Q by rho V. So now I am substituting the delta V as delta Q by rho V and cross multiply here the rho V. So delta Q is equal to rho V into delta S into delta L. Delta S into the delta L. Let the charge is moving in x direction with velocity v bar, and thus the velocity have only x component. Only x component Vx. Okay. The velocity is denoted by a small, let us say, this one. In the time interval, at the element of charge has moved through the distance delta x in x direction. The direction is normal to the surface delta s, and hence the resultant current can be expressed as what is the change of current? The change of current delta I is equal to the change of charge with respect to the time, my dear. Current I, the change of current with respect to the change of charge with respect to the time. The moving of charge carriers produces a current. Okay. Through any conductor, there is a movement of the charge carriers produces a current. The change of current is equal to the change of the charge with respect to the time. Got it, my students? So what is that delta Q is equal to? We already know that delta Q is equal to rho V, delta S, and the delta L. The delta L, but now the delta Q is equal to rho S, rho V, delta S, delta X, as the charge corresponding the length delta x is more and the responsible of the current. So previously, that at the origin without moving, that is a delta L. If it is in the x direction, the charge is moving in x direction with velocity v bar, that delta L is changed as the delta x. Okay, now we can substitute the value of delta Q in the change of the current, the change of charge with respect to the delta T, or with the change of charge with respect to the time. Now, the change of current, the incremental current, or otherwise delta I is equal to delta Q. We already know rho V, delta S, and actually it is a delta L. The delta L, now it is a movement occurs there from its origin. It's considered as the delta X and a whole divided by the delta T. Now again, you can see this is a function, the change of x with respect to the time, dx by dt, x is a displacement. Consider the x is a displacement. X is the displacement, and v is the velocity. V is velocity, and a is acceleration. A is acceleration. We know the velocity is the t velocity v is equal to change of displacement with respect to the time. Change of displacement with respect to the time. And acceleration is change of velocity with respect to the time, dv by the dt. So now use this formula, the velocity v is equal to the change of displacement with respect to the time. Now, if I take the small differential increment, or the v is equal to the velocity in x direction, v is equal to a small incremental x with a small incremental time to t, delta x by the delta t, or change of displacement with respect to the time. Okay. You see here, delta x by delta t is a velocity in x direction, that is a vx. Velocity in x direction, that is a vx. So replace delta I is equal to rho v delta s, and the delta x by delta t is equal to vx. The velocity v is equal to change of displacement with respect to the time. Because it is in the x direction, there is a suffix x also. Vx is equal to x component of velocity v bar. X component of velocity v bar. Okay. Now, but the previously in the, we know the relation between of current and the current density is delta I is equal to j bar into delta s. Delta I is equal to j bar into delta s. Or otherwise, the I is equal to integral j bar dot ds bar. It's a formula for a change of the current with respect to the time. The formula, the change of the current with respect to the surface, delta S is equal to current density j bar. Using this relation, now what is a delta I is equal to? Delta I is equal to j bar into delta S. So substitute here the delta I as j bar into delta S is equal to rho v into delta S into Vx. What it matters. So delta x and delta x cancel, and now the j bar is equal to rho v into Vx. J bar is equal to rho v into Vx. So see, it is a vector and it is in the x direction. Let us take it is also the rho v is equal to rho v into Vx. So x component of j bar in this case has only the x component. So we take that is a x, jx. Otherwise, it's having only the magnitude, you can say the J is equal to, or Jx is equal to rho V into Vx. Rho V into the Vx, where the Vx is the x component in the velocity V bar and Jx is the x component of the J bar. Follow my students. So now we got this relation Jx is equal to rho V into Vx, where Vx is the x component of the velocity V bar and Jx is the x component of the J bar. Okay. In this case, J bar has only the x component. In general, the relation of J and rho V is expressed. In general, it is not in the x component, means J bar is equal to rho V to B. As I said that is a J bar x is equal to rho V to x component. In general, we can say that it's a J bar is equal to rho V to B bar. J bar is equal to rho V to B bar, where V bar is a velocity vector. Such a current is called conventional current, and the current density is called conventional current density. Got it, my dear student? Such a current is called conventional current, and the current density is called conventional current density. In this connection, the convention current density is linearly proportional to the convention current density is linearly proportional to the charge density and the velocity, the volume charge density and velocity with which charge is transferred. The definition, see, the conventional current density J bar is linearly proportional to the charge density and the velocity with which the charge is transferred. The charge density, volume charge density and the velocity bar. Remember, my dear students, it's a very, very important relation is there. The J bar is equal to rho V into V bar. And previously, the relation between of current and current density, the current and current density is J bar is equal to, not the J bar, I is equal to integral J bar dot ds bar. Is a relation between of the current and the current density. Is a relation between of the current and the velocity. Current density and the velocity. Okay. So both relations is very important. Now, go for the another important topic is a continuity equation. So another important topic is a continuity equation. And these two, the relations between of J bar and the I is equal to integral J bar dot ds bar, or I is equal to J into ds. Using that relations, we can derive the continuity equation here. So the continuity equation of a current is based on the principle of conservation of the charge. The continuity equation of current is based on the principle of conservation of charge. This principle states that, you see, this principle states that the charges can neither be created nor be destroyed here. Consider a closed surface S with a current density J bar, then the total current crossing the surface is given by, consider a closed surface and with the current density J bar, the total current I crossing the surface is given by I is equal to integral J bar dot ds bar. There is a relation between the current and current density. The current flows outside from the closed surface. It has been mentioned earlier that the current means the flow of positive charges. Okay, flow of positive charges, and the current I is constituted due to the outward flow of positive charges from closed surface S. According to the principle of conservation of charge, there must be a decrease of an equal amount of positive charge inside the surface, that is a closed surface, as the outward rate of flow of positive charge is get balanced by rate of decreasing of charges inside the closed surface. Okay, the charge inside the closed surface is considered as Qi, and the change of that charge with respect to the time inside the closed surface, because it is a current that is passing through the closed surface. The current flows outwards from the closed surface. Whenever if it is changes, there is a decreasing the equal amount of positive charges inside the closed surface. What it matters, students? That is a change of the current, the change of the charge QI by with respect to the time, the rate of decrease of charge inside the closed surface, dQI by dt. The negative sign indicates the decreases. Okay. Inside the closed surface, the negative sign, whatever we are using here, that is a decreasing of the charge. The negative sign indicates the decreasing of the charge, whichever it is enclosed, the closed surface. Due to the principle of conservation of charge, this rate of decrease is the same as, remember my dear students, it's a very important point. This rate of decrease is the same as the rate of outward flow of charge. The rate of decrease is the same as the rate of outward flow of the charge. Nothing but it is a current term, which is a current. The current I is equal to, we know the relation is J bar dot ds bar. That is equal to whatever we are saying. There is a charge with respect to the time is changes, and the negative sign indicates the decreases of charge. So I is equal to minus dq by dt. That is also equal to the J bar dot ds bar. Okay. This is an integral form of the continuity equation of the current. The negative sign in the equation indicates the outward flow of current from closed surface because of decreasing in the inside, and it balances the outside. So that is the negative sign we are indicating. If the current is entered in the volume, then the integral J bar dot ds bar, I'm modifying the equation integral J bar dot ds bar, and it's a minus I is equal to dq by dt. The point form of the continuity equation can be obtained from the integral form using the divergence theorem. Now you can get here divergence theorem or the Stokes theorem, converting the surface integral to form the volume integral. I already told the Maxwell's equation saying that d bar dot ds bar is a gas law. We are saying the change of the differential d bar dot ds bar, the surface integral, to the volume integral. We can use the del dot, whatever the term is there here, the d bar. So del dot d bar into rho v, not the rho v, sorry. Del dot d bar into dv, not the rho v, dv, sorry. The surface integral is changes to the volume integral by using the divergence theorem or the Stokes theorem. Now, similar way, here we have the surface integral is a J bar. J bar dot ds bar is equal to integral rho v, integral volume integral del dot, instead of d here the j is there, so j bar del dot j bar into dv, del dot j bar into dv. You see here the volume integral del dot j bar into dv. So it is equal to the minus I or the minus dq by dt. So I am using the minus, the change of the charge with respect to the time. But the current, and the negative sign indicates decreasing of current in the inside of the closed surface. Okay. See, minus dq by dt is equal to the volume integral of del dot j bar into dv. But we know, see, the change of current charge with respect to the volume dq by dt is equal to, the rho v, the charge density. volume charge density. So dq by dv is equal, or otherwise dq is equal to rho v into dv. Got it, my students? Or apply the integral on both sides, it becomes of the left hand side it's a q, and right hand side it becomes of the volume integral of rho v into d. So that q is equal to rho v into d. Okay. Then use the equation, the integral del dot j bar dv is equal to, substitute the q in this equation, the d by dt of qi. Okay. See, I'm using this equation, the integral, the volume integral, that too, volume integral del dot j bar into dv, del dot j bar into dv is equal to minus d by dt of what is the q we got here? The volume integral of rho v into dv. Rho v into dv. Same equation we got. Got it, my students? Now bring that it is a derivative part in the inside becomes of partial derivative. Okay, partial derivative is equal to minus the volume integral of bring this d by dt the inside of the integral, it becomes of the partial derivative dou rho v by, here the dt is there, dou t, the dou rho v by dou t into d, and here the minus is there. Now on both sides we have the volume integral del dot j bar dv, and here dou rho v by dou t into d. So remove the volume integral on both sides. Now it becomes of del dot j bar is equal to minus dou rho v by dou t. The continuity equation. See here, same thing. Is a point form or the differential form of the continuity equation of the current. This equation states that the current or the charge per second, the diverging from a small volume per unit volume is equal to the time rate of decrease of the charge. The time rate of decrease of charge per unit volume at every point. The decrease is a negative sign here. The time rate of decrease of charge per unit volume at every point. Okay, this is a very important matter, students. The continuity equation. Now, till now we learn that there is a relationship there. I is equal to the relation between of the current and the current density. I is equal to j bar dot ds bar. And another one is there. The current I is equal to minus we want the q dq by the dt. I is equal to minus dq by dt. And another one is there. Continuity equation del dot j bar is equal to minus dou rho v by dou t. Dou rho v by dou t. And the surface integral to the volume integral means you can use the del dot, whatever the term is there, you can use that and keep the volume integral. Okay. And another one is there. The relation between of current density and the velocity, that is j bar is equal to rho v into v bar. This is also very important. J bar is equal to rho v into v bar. So all the relations we have in the current and the current density. I is equal to j bar dot ds bar, and that I is equal to minus dq by dt, and as with the continuity equation, del dot J bar is equal to minus dou rho V by dou T, minus dou rho V by dou T. And the J bar is equal to the relation between of current density and the velocity in x direction, or the component of x. As actually it is a Jx bar. Jx bar is equal to rho V into Vx bar. Both are in the x direction, so only the J bar is equal to rho V into V bar. Okay. The next topic, we go for the steady state conductor. Steady state conductor. For a steady state it's not the conductor, steady current. For steady currents which are not as a function of time, dou rho V by dou T is equal to 0. Dou rho V by dou T is equal to 0. Sorry, it is a current, not the steady current. For steady currents which are not the function of the time, dou rho V by dou T is equal to 0. So according to the continuity equation saying that del dot J bar is equal to dou rho V by dou T. So for steady currents which are not a function of the time means that the value is 0, del dot J bar is equal to 0 for the steady current. For such currents, the rate of flow of charge remains constant with respect to the time. Okay, the rate of flow of charge remains constant with respect to the time. The steady currents has no sources or the sinks, and it is a constant. Simply saying it is a zeros. Then the conductors. Let us study the behavior and the properties of the conductors. Under the effect of applied electric field, the available of free electrons start moving. If any conductor, we can apply the electric field on side. There is a flow of electrons. The free electrons starting moving. The moving electrons strike the adjacent atoms and rebound in the random directions. This is called a drifting of the electrons. Drifting of the electrons. After some time, the electrons attain the constant average velocity is called drift. Okay. See the relation. So the velocity Vd, drift velocity, the current constituted due to the drifting of such electrons in metallic conductors is called the drift current. The drift velocity is directly proportional to the applied electric field. How we get this one, the drift velocity, the moving of the free electrons. Okay. The drift velocity is directly proportional to the applied electric field. So V T bar is proportional to the E bar. The electric field is the electric field intensity E bar. The constant of proportionality is the mobility of electrons, that is a mu E. Mu E, it is a positive for the electrons. V T bar is equal to minus mu E into E bar. The constant of proportionality constant is the mobility of electrons in a given material is denoted as mu V. It is positive for electrons. Okay. The negative sign indicates that the velocity of electrons, is against the direction of the E bar. You know, always the electrons flow is in one direction and the applied current voltage is in the other direction. The negative sign indicates the velocity of electrons is against the direction of the electric field. Okay, so that is a negative sign here. The Vd bar is equal to minus mu E into E bar. The mobility is a velocity per field. Velocity per field, nothing but electric field. Velocity is a meters per second and the field is volts per meter, and it becomes of meter square volts second. The mobility is measured in the square meters per volt second. In square meters per volt second, the typical values here, the 0.0012 for aluminum and 0.0032 for copper. Okay. And now we know that one of the relation is there, the velocity and the current density, J bar is equal to rho B into B bar. J bar is equal to rho B into B bar. But in their material, the number of protons and electrons is same. It is always electrically neutral. And so rho B is equal to 0 for neutral materials. Rho B is equal to 0 for the neutral materials. The drift velocity is the velocity of free electrons. Hence, the Voigt relation can be expressed as, you see, the rho V I am taking as a rho E, a charge density due to the free electrons. The charge density, the rho V is the charge density, the volume charge density actually. Now I am taking that is a E. Rho E is the charge density due to the free electrons. And due to the drift velocity, so the J bar is equal to rho V into B is becomes of J bar is equal to rho E into VD bar. The VD is the drift velocity. Got it, my dear students? Now, what is a rho E here? Rho E is equal to, we know, the VD is equal to the drift velocity is minus mu E into E bar. Minus mu E into E bar. So VD is equal to the drift velocity, the vector component, minus mu E, the mobility of free electrons, and the electric field intensity E bar. Okay. Now, you can substitute here the VD bar is equal to, VD bar is equal to, in the J bar relation, J bar is equal to rho E into VD bar. What is the VD bar here? Minus mu E into E bar. Minus mu into E bar. So the J bar we got as J bar is equal to minus rho E mu E into E bar. The relation we got now, the current density and the electric field intensity with a constant of minus rho V to mu, where rho E is a charge density due to the free electrons and mu is a mobility of free electrons. Got it, my dear students? And this is nothing but it is a J bar is equal to minus the sigma here, the sigma into E bar. Okay. Not the minus, the sigma is equal to minus rho V into mu. Now you can derive this expression, the point form of the Ohm's law. You see here, J bar is equal to, it is a sigma into E bar. That sigma is nothing but the conductivity of the material. The relation between the J bar and E bar can also be expressed in terms of the conductivity of the material. Thus, for metallic conductor, J bar is equal to sigma into E bar. Now, what is the sigma? Sigma is equal to minus rho E into mu E. Is another relation. J bar is equal to sigma into E bar, where sigma is the conductivity of the material. Conductivity of the material. This equation is also called the point form of the Ohm's law. Okay. So these are the values of conductivity of aluminum 3.8 to 10⁻⁷ and the 5.8 to 10⁻⁷ for the copper. It is in the ohms per meter. Sigma is equal to minus rho E into mu E. Its conductivity in terms of mobility of charge density of free electrons. Okay, forget about the remaining of the things. As the temperature increases, the conductivity decreases and the resistivity increases. Remember these also, the value is very important. As the temperature increases, the conductivity is decreases. If the conductivity is decreases, definitely there is a increasing of the resistivity. Okay. Now, to find the resistance of a conductor here, consider the voltage V. Consider a voltage V. The current is in the direction and the flow of electrons is in the opposite direction. The E bar is the another direction. Okay. Let us here, it is a conductor. It's a conductor, my dear students. Just like this. having the length is L. It's a conductor having the length L. Apply the voltage V. The free electrons, the direction is towards negative direction, and the field is in this direction, and the current flow is also in this direction only. That is, current is called conventional current. Consider that the voltage V is applied to the conductor of a length L. So this is a conductor. We are applying the voltage V to the conductor of length L, capital L, having the uniform cross section S. That's total surface here. Uniform cross section S, as shown in the figure here. The direction of E bar is same as the direction of conventional current. The E bar direction and the current direction is both are the same, and only the electron's direction is different. The direction of conventional current and the direction of electric field is the same, which is opposite to the flow of electrons. Which is opposed to the flow of electrons. The electric field is applied is uniform, and its magnitude is given by. If the electric field is uniform, the magnitude is given by the E is equal to applied voltage and the length of the conductor. The length of the conductor. Okay. So E is equal to V by L. E is equal to V by L. We know the relation between of the current and current density as in the integral form. I is equal to integral J bar dot ds bar. Or in the point form, it is the same as I is equal to J into S. J into S. A little bit the confusion is there we have, and now the change of the current Ti is equal to the J into ds only. If I am using that is a J bar dot ds bar, apply the integral is there. The integral I di is equal to, when these two are in the vector form, the dot product we are getting. So integral, surface integral J bar dot ds bar. So I is equal to, we got the J bar dot ds bar on. J bar dot ds bar. Got it, my dear? So both are the same. The I is equal to integral J bar dot ds bar is equal to J into ds. J into S, not the ds. J into S. The current direction is normal to the surface S. So using this relation, I is equal to Js, J is equal to I by S, that is equal to I by S, that is equal to sigma into E. Now only we derive the expression. Okay, the point form of the Ohm's law. Not the Ohm's law, sorry. You see here. Point form of Ohm's law only. J is equal to sigma into E. So I by S is equal to sigma into E, and J is equal to, using the 8 and in the equation 10, E is equal to, what is the E is equal to? V by L. See, I know the E is equal to the applied voltage by the length of the current. The electric field E is equal to applied voltage by the L. And we know the J is equal to integral form J bar dot ds bar, or otherwise the point form J into S, not the J, I is equal to. So what is a J now? J is equal to I by S. I by S, and that J, according to the Ohm's law, sigma into E. J is equal to sigma into E, and E is replaced the V by L. Now the J is equal to sigma into E is V by L. V by L, where is the sigma is the conductivity of the material. J is equal to sigma V by L. Okay. Now the V is equal to, now cross multiply this, V is equal to J L by sigma. So L is multiplied with the J and take the denominator of the sigma cross multiplying JL by sigma. Got it, my dear students? So what is the J again? J again in terms of the current I is equal to J into S. I is equal to J into S. So J is equal to again I by S. I by S. Substitute that here. I L. Now I am taking here the I by J means I by S. I by S and L by sigma. So J is replaced with I by S and L by sigma is there. Now rewrite this function totally again. L sigma into S into I. See the L sigma into S into I. Got it, my dear students? So V is equal to, we got L sigma into S into I. So we know the relation is V is equal to IR. V is equal to IR. Now what is R is equal to? R is equal to L by sigma into S. This is the relation.